Hello guys, today continue our study on sequential circuits in Verilog. We're going to learn how to create single port RAMs and dual port RAMs. Okay? Following the same format of the course, we're going to learn how to create on the lab the Verilog code to create those RAMs, and how to create a test bench to exercise and verify if what you created is actually working as expected. Okay? I'm going to switch now to a better explanation on every one of the topics that we're going to learn. Okay? Hope you guys like it. Let's start with the single port RAM. The single port RAM is this block here, which have as inputs the data in, address, write enable and clock, and as output the Q out. The main idea is that in the positive edge of the clock, if the write enable signal is true, we're going to insert a value in the address pointed here as in address with the value inside in the in. Okay, so you can imagine that you are populating a vector, okay, a vector with a fixed size, and in every position of this vector you are inserting the values in the in. Okay, then in a second moment you can read those values as well, just pointing out the position of this vector that you want to read, and then the value come out in Q out. Okay? The main difference now, if you switch to the dual port RAM, you can see that we have two distinct parts, okay, called A and B, which allows you to write and read at the same time in different address. This is basically the main difference between the dual and the single port RAM. The dual port RAM will allow us read and write on different address in the same clock. Okay? Here in this case, if you want to read and write for two different addresses, you're going to need two clock cycles. Okay? We're going to start by creating a single port RAM in Verilog, then we're going to switch and see how we can do a dual port RAM and see how this can be done. Okay? In the next video, we're going to learn how to use FIFOs, and FIFOs especially use the dual port RAMs as well as video memories and stuff like this. Okay? Okay guys, let's see now how the RAM will work with a little bit of more detail. Okay? Here we have a RAM block, okay, which has 8 positions, and we can store words that have up to 32 bits. Okay? And as usual, here we put that this block RAM will execute when we have the rising edge of the clock. And here in this case we want to push into the value A in the first position. Okay? In order to do that, we would put the write enable to 1, the data input to the value that you want, A, and the address to be 1. Okay? Now imagine that we want to read this value here. Okay? We don't want to write in the RAM, we just want to read. We put the write enable to 0, we put the address to 4, and in our output we're going to receive D. Okay? Now imagine the other case. Imagine that you want to write, for instance, in the position 7. Okay? The position 7 has already stored a value C1. Okay? And we want to know, for instance, we want to write a value FF, but we want to know what we're going to have in the Q out. Okay? As usual, to write into the RAM, we're going to put the write enable to 1, the data input to FF, and the address, in this case, to 7. Okay? Now, we can have two outputs in Q out, and this depends on how you want to develop your RAM. Okay? You can put the Q out to receive the old value that has already been stored in the memory, in this case C1, or you can have the new value that you're putting at this exact same moment. Okay? This behavior sometimes called read before write, okay, if you want to get the old value, or write before read if you want to get the new value that you are adding now. This will be important in future sections when we learn how to do image processing in FPGAs, that we're going to learn something called line buffer, and in the line buffer we want to have the old value. Okay? Before we continue, in order to create arrays in Verilog, okay, for instance, imagine that you want to create an array with 8 positions, okay, And every element of this array is going to have 32 bits. You create in this format here, okay? It can be a while or red, in this case is a red, okay? 31 down to 0, the name of the array, and this number of elements in the array, in this case 8, okay? Just to show a little bit, this for instance is an array of 8 elements with every cell that could hold up to 32 bits. Okay guys? So let's start our design with the single port RAM. This design is a simple 8 size with 32-bit data word single port RAM. It has as inputs the clock, write enable, address and data in, and as output the data out. Now we are declaring an array in Verilog with 8 positions, and every position, every cell in this array are going to have 32-bit wide. The syntax is there in the left. You guys can see how we can declare an array like that, and as also a visual representation of an array. So we have 8 slots. Every slot has 32-bit vector, okay? And we're going to, after this, we're going to create an always block to handle the read and write. Now we are going to create an always block that is going to execute in the rising edge of the clock, and this always block is going to be responsible to write elements in our RAM. Okay, if write enable is true and the clock edge is positive, we're going to add a value in the array that we created. And in parallel to all this, we have an assign block that is going to get a value from the vector from the array that we created. By the way, the always block and the assign, they really run in parallel, okay? And I'm just putting some comments in your left just about how we can see if the single port RAM is in the mode read before write or write before read. Now we are going to create our test bench. By the way, the same recipe for test bench. First, declare the device under test. Second, instantiate your device under test. Third step, initialize the values of the inputs to a known state. Generate the clock if it's the case of a sequential test bench, and you add some stimulus. Okay? I'm going to copy and paste to get some time in this test bench, but we are going to check that it's quite simple. We just write in all position memory a known value, then you read, we verify if the values do match, and then we try to write in a previous position that we wrote before to verify if the single port RAM that we created is in the mode write before read or read before write. So now that we paste, that's it. We write 8 positions. in a for loop. Okay, we write I don't know, from 1 to 8. Okay, yes, in something like this. Then we read these values and we verify if the values that we store are the same as the what we wrote. Yes, and then we just try to write in the position 5 some value. Okay, in this case 99, and you verify if you receive the value that we just put right now or the value that was before. Okay. Now just let's put the simulation to run. By the way, just remember, after you change the inputs, in order to fetch a result from the simulation, you need to have some kind of weight. In this case here we are using the pos edge, the wait pos edge, just to wait an edge of the clock. Okay, now let's see the waveform. We're going to just do a zoom out to see all the values, and we can see that indeed our memory is working. So at every rising edge, we store some value, and then we can read those same values, and in the position 5, we write 99, and we get the value 99, which is the new value. So as expected, we created a memory that is right before read, or get the new value when you store something in a position that has already a pre-stored value. Now let's just change our design a little bit to be the read before write type. We're just creating here a reg variable that is going to be actually a register. Then on our always block that we do the write into the memory process, we also going to store this value in this register, and when we read, we're going to read this register. So it's really going to be the read before write behavior. So if we test this simulation right now, we're going to see that instead of getting the value 99, that is the value that we are pushing now, we're going to get the old value. Okay? I'm just putting some comments there just to help us a little bit to understand what is going on, but that's it. In every rising edge of the clock, we're going to store the current position that we have in memory. And in our assign block, we're going to use this register. So we're going to get the value that were there at the time. Now let's run the simulation again, and let's go to the end part of the simulation just to verify what is the last value. Okay, and you see that the value is 10, which is the old value that we store, disregarding the value that we add just now. The value 99 will be stored in the memory, but we're going to return the old value that was there. Okay, this behavior is quite useful, for instance, for line buffers. When we're going to see how to do image processing FPGAs, this will be a nice stuff to have. Okay, now we are creating the dual port RAM. By the way, the only difference now is that the dual port RAM will allows you to read and write in different address, okay, at the same edge of the clock, something that's not simply not possible in the single port RAM. And the dual port RAM has a lot of usage, for instance, in FIFOs and stuff like that, that you need to write and read and a different address at the same rising edge of the clock. Okay, here we're just adding some parameters to the design. Later we're going to create an IP block from that. By the way, is what we're going to discuss in the next video. And as inputs we have clock write, enable A, write enable A, address B, data input A, data input B. A and B, by the way, are the ports. And as outputs, the out A and the out B. Okay? So basically, in the same edge of the clock, we can put different address in the port A and B, and we are really going to access our array at the same time at different positions. Okay. By the way, doing dual port RAMs is the only case that you can have a always block that is going to write at the same variable at the same time. Normally, it's not a good idea to have a always block. I mean, it's not a good idea to have two always blocks changing the same variable. Okay, but in order to do dual port RAMs, you need it. Is basically the idea. Okay. Here again, we're just showing how to declare an array, okay? And this array is going to be accessed by two always blocks. One that's going to have the address of port A and the other in the port B, okay? Now, we doing the always block for the port A. By the way, this always block is going to execute in the rising edge of the clock. And if the write enable of the port A is true, we're going to write something in the array that you created, the ramvec variable, at the address pointed in the port A as well, address A in this case. Okay, and you're going to have then another always block that you do the same thing for the port B. By the way, in this same always block, we are also going to handle the read of the variables. In this case, in this dual port RAM, we also want to do we will do the read before write behavior. So in this same always block, basically we are outputting in the out A the variable that is the pointed in the vector. By the way, we are actually exercising the fact that in an always block, the signal that is going to be changed, the variable that is going to be changed, is only going to be changed in the end of the always block. So if you are going to change the out A in the end of the always block, we're actually going to return the old value that was there, not the new one, which basically will do the job that we want. Now we just copy and paste to do the same thing for the port B, and we are quite done. We just go now and write a test bench to see if our guy is working as expected. So we just synthesize to check if everything is okay, but let's create our test bench, by the way, okay? So let's start. We're just going to create a new simulation model. Just delete some comments and I will paste a predefined test bench. By the way, the recipe is the same, so nothing new, nothing fancy. The only difference is now for the for the dual port RAM, instead of using two for loops, we're going in the same for loop with half of the clock needed. We're going to store some values in all the memory. As we are going to do half on the port A and half of the port B, we actually can do everything in half of the clock needed.
Okay, just instantiating, putting some initial values in the test bench, creating the clock, and now in this for loop we're going to write 4 times the values 15, 14, 13, and 12 in A, and 19, 18, 17, and 16 in B, in the address 0, 1, 2, 3 in the port A, and 4, 5, 6, and 7 in the port B. So actually going to put 8 values with just, in theory, 8 ticks of the clock. Oh, sorry, 4 ticks of the clock. Okay? Then we're going to write 8 times sequentially in the port A, if we really have the values that we put there, which is 15, 14, 13, 12, 19, 18, 17, 16. And the last thing that you're going to do is going to verify if you are in the mode read before write, just by writing in the address 5 some value like 99 and verify if you get the old value. Okay, so let's run our simulation, run the behavior, and let's see in the waveform that we generated if we are actually doing. I'm just changing the radix, the data type of the variable, just to help us to read a little bit more, delete some signals that we don't need. And you can see already that yeah, things are running fine. We actually reading the stuff that we put there, and actually in the order that we put there. This is quite important. And in the value 5 we're getting the value 18, sorry, in the address 5 we're getting the value 18, which is the old value that we store on that position. So everything's fine, guys. So this is what we have to talk about dual and single port RAMs.